Welcome to Precalculus. We're going to do some things in section 2.6, mainly some examples. So assuming you know the theory about how to do the upper analysis to find the zeros of the function, of a rational function, and the lower analysis to find the vertical asymptotes, and then the comparison of numerator and denominator degree to find the horizontal asymptote, we're going to do a few examples. So let's start with a pretty basic one. And it's going to be f of x equals 2x over x plus 2. Okay, so in the what I'm calling upper analysis, looking at the numerator, what makes the numerator 0? Well, 0, right? So that means if you set that equal 0, you get 0. So therefore, the x-intercept is 0. In other words, it goes through 0, 0. Which also means the y-intercept is 0. That's good to know. So we'll go through the origin. Let's do a lower analysis. What makes a denominator equal 0? Well, negative 2. Negative 2. So therefore, there's a vertical asymptote at x equals negative 2. Okay, and then our comparison step. Comparing the degree in the top and bottom, there's a tie, right? Because the numerator is first degree, the denominator is first degree. So it's the ratio of leading coefficients is our horizontal asymptote. And the ratio of the leading coefficients is, get rid of that, is 2. So it's going to be y equals 2. There we go. It's hard to do the squiggle underline on here, so that's what I'm trying to do. So let's actually try to graph this now. So if you were asked to sketch this from the beginning, we'd want to make sure we could see x equals 2. We want to make sure we could see y equals 2. Yeah, x equals negative 2 and y equals 2. So I'm going to go over 1, 2. If I can do this decent on this iPad, you can do it even better on your paper. So that's y equals 2 and x equals negative 2. And it goes through the origin. So here's what I advise you to do, because after you've seen a few of these, you know it's got the two branches typically in opposite quadrants. So I'm guessing this is going to be in this kind of lower right and upper left. But let's test a few. So what I advise you to do, and I'm going to show you a list of things here in a moment, is make a list. And we already know 0, 0 is on there. And we're going to see if we can find some other points. I typically would say pick some points on the same side of the vertical asymptote and near the vertical asymptote. Like negative 1 would be a great example. And we're going to plug it in the original function. And that would give us negative 2 over 1, negative 2. So that's going to put us down, I should be labeling these, shouldn't I? 2, negative 2. So that's going to put us right here. And that's about what we would expect. What else could we graph? We could probably plot, how about 1? 1 would be 2 over 3, 2/3. So around there. And that's probably enough to get the idea of what it's going to look like. It's going to look like this. Oh. And then over here you're going to graph in the upper left branch smooth and symmetric. So I'm going to kind of put a point there. That's kind of the same distance from the intersection of the asymptotes as the other one. And then it's just going to go through. This isn't something for science. This is just a sketch. We just want to see that it's a rational function. It's got its two branches. We have at least a few points. We include the asymptotes. We include the intercepts. There we go with the sketch. Let's try another one. I go to the next page. Okay. Let's try one with an extra step that we're going to have to include. If we had a g of x equals x plus 3 over x squared plus 4x plus 3. what do you think of when you see this problem? It's all over that. Sorry, it's really hard to read. That's x plus 3 over x squared plus 4x plus 3. What do you think of? Well, I hope you're looking at the denominator and thinking, that may factor, because we always want to factor. If we could simplify it, let's do it. In fact, if you were to do your lower analysis, you would factor that, and you would find out one of the factors is x plus 3, which is in the numerator. So let's go ahead and do it right now, and really you must do this right now. And I'm going to show you a series of steps in a moment, and one of those steps is in the beginning is to factor as much as possible, and if you can, cancel. So that's pretty awesome. We're now left with 1 over x plus 1. Now I should make the note, in the original g at x could not be negative 3, right? Because if x were negative 3, you'd have a 0 in the denominator. That's not good. So, can x be negative 3 now? Well, according to this, it can. But really our equation was what's up here. And it couldn't be there. So, you'll frequently see in books, they might put a little comma and say, this is right, except, x actually can't be negative 3. That just wouldn't make sense. So you can use this 1 over x plus 1, just don't let x be negative 3. You might wonder, what's going to happen there? Is there going to be a vertical asymptote? That's just weird, right? Well, let's do our quick analysis here, and we'll see what's going to happen. The upper analysis, 1 can't be 0, so there are no x-intercepts. The lower analysis, when is x plus 1 0? When x is negative 1. And that is our, let's see how I'm going to label this. That's our vertical asymptote. And then our comparison step, I'm just looking at this simplified form right here. But either way, the denominator is greater degree, so the horizontal asymptote is going to be y equals 0. So this is kind of a boring graph. Let's see. So here we have this x equals negative 1. And then the x-axis is an asymptote. It's kind of hard to see that. And we don't even have any intercepts. We have 0 points to put in. Let's plot a few. Maybe, okay, usually I say something near the asymptotes. How about 0? 0 would be 1. How about 1? 1 would be 1/2. 2 would be 2/3, so on. So 0 is at 1. 1 is at 1/2. 2 is at 2/3. What about 1/2? 1/2 would be at, what is that? 1 over 3/2, which is 1 over 3/2, which is 2/3. Oh, 2/3. I meant to say negative 1/2. Negative 1/2, because I want to get something closer to the asymptote, would be 2. So you kind of see what's happening here. There's an asymptote on either side, so it's going to look something of this sort. Again, we're just making a sketch. Smooth and symmetrical about here, maybe. Just making a sketch. What about that whole x can't be negative 3 thing, though? Well, where is x is negative 3? Probably around here. What's happening there? Looks pretty normal to me. Well, this is an odd case where when this happens, where you have a rational function and you have a factor in the numerator cancel with a factor in the denominator, you can graph it in this simplified form, except when there's a cancellation. That means you're going to say this, there will be a hole at x equals negative 3 in this case. So actually I drew a hole. If you were to graph this in your calculator, you would notice, not really a hole, but you would notice there would just be a gap. Let's see if I can use my eraser here. Not quite that much of a gap. But if you zoomed in, you would notice, let's see, 1, 2, 3, and I'm probably not going to be able to do this with this pen, but you'd notice a little gap there. I mean, it'd be much smaller than that. Typically, though, we don't just have this random tiny gap, we use a circle to show that there's a hole there. And so there would be a hole at x equals -3. So that's going to lead us to a kind of a summary statement of what we can do here. So let me do another slide. Maybe we'll end here. Let's end here. So hopefully that helps. I'm going to come back and do one more with our summary statement of kind of pointers for graphing, and then I'll probably do a special one with slant asymptotes. But you've seen much of the important stuff here. So hope to see you in the next one, though.